Hello and welcome back. Thank you so much for being here at 4 o'clock. For those who've been with me all day, congratulations. For those who've just joined, thank you as well. And we hope to cover the last topic for the day. It's a beautiful topic called complex numbers. And believe it or not, my guess is that you've used complex numbers a lot already today. Most people don't know what complex numbers are for, and most people aren't told, but believe it or not, you use them probably daily, several times a day, and they're hugely useful. And I'll explain what you use them for somewhere along the way during this session. So thank you very much for being with me. I'm going to start now by sharing my screen again. I'll just show how that works. And hopefully you can see a topic called complex numbers. So hopefully you have the notes there. If you don't have the notes available to you, they're available online at griffith.ie. Just go to the website, griffith.ie, and on the first page there's a link to the maths course, and on the maths course there's a link to the resources. So you should be able to print off the notes for today, for Thursday. So we're going to look at complex numbers, and this is a guided tour. There's always a question or two on complex numbers, and we'll go through every question type that's come up before and cover what they're allowed to ask. So we're going to start with complex numbers, and I'm going to start with some terminology. So that's the first phase. So a complex number is defined as something with two parts in it. It's got 5 plus 12i is a complex number. It's a number with sort of a real part, and then what we call a real coefficient and an imaginary number. So in the past, if we think about how sort of boring numbers were, most of the numbers are on a thing called a number line. And we think about the number 0, 1, 2, 3, 4, and numbers just go along the number line. You might get minus, minus 2, minus 3. You might get an interesting number along here like pi or something like that, or the number e might pop up along here. But really it's pretty boring. It's just all the way to the right, all the way to the left. You never move around. So the number line is just a line. It's just that. But with complex numbers, you can number out here, or a number here, or a number there. You can still have them on the line as well, but they can be all over this two-dimensional space. So that's news about complex numbers. So there's always in two parts. There's a real part and an imaginary part. The real part is the same as your ordinary number, like 1, 2, or 3. And the imaginary part is maybe the number 1, 2, or 3, but followed by the letter I, where I is an imaginary number, the square root of minus 1. So let's just look at the area now. So we look at complex numbers, and we decide that it's in two parts, a real part and an imaginary part. The set of complex numbers in terms of set theory is given by the letter C, and that's equal to that there. Okay. The Argand diagram, we have an imaginary and a real x instead of x and y, but it's exactly the same. 2, 8, instead of saying 2, 8, which we would be used to for x, y, we say 2 plus 8i. So the 2 is first, the real one is first, so that's the horizontal or the x-axis we're familiar with, and then the y one, the vertical axis, is second. So 2 plus 8i. That's 3 plus 4i. If we wanted 4 plus 3i, we'd go out 4 first and up 3. That's 4 plus 3i. So the order does matter, and the first number is the real value, okay? And the second, the number that's on the horizontal line, and the other is the vertical. The Argand diagram actually is in all 4 quadrants. So you could have a number down here that would be a minus real number and a minus imaginary, minus 5 minus 2i, or it could be up here 2 plus 2i, or in any of the other 4 quadrants. So this number here, let's say 4 plus 2i, the only way to get to 4 plus 2i is the real value has to be 4. It can't be anything else. And the imaginary part has to be 2i. So that's the way it works. So when you say that a, let's say that if you've got a complex number z1 called a plus bi, and z2 is c plus di, if they're the same number, if they're equal, then the real parts have to be equal and the imaginary parts have to be equal. You can't compensate. You either, the horizontals must be the same and the verticals must be the same if the numbers are going to be overall the same. Another way of looking at the Argand diagram is to consider how far it is from 0, 0. So for example, if you look at the number line, you might be used to the number line and say, well, this is the number 1, 2, 3. It's a distance of 1, 2, or 3 from 0. Or this point here, minus 3, is 3 away. And sometimes we use the term, the length, the absolute value. So if we say the absolute value of x is 3, then it could be minus 3 or plus 3 because they're both 3 away from 0. But with the Argand diagram, given that can be all over the place, this point here is the length of it, it's 12 out and 5 up. So 5i, 12 out, 12 plus 5i. What is the overall length of that? How far is it from 0, 0? Well, we can do that by drawing on a different part of our course. Because these are perpendicular, this is a 90-degree angle. Because that's a 90-degree angle, it's like a right angle triangle. Therefore, Pythagoras applies. So the length of this value here, if we were to look at z as that being the complex number z or z1, we would find that the length of it is 12 squared plus 5 squared square rooted. Because the square of this is the square of that. That turns out to be the square root of 169 or 13. So drawing the Argand diagram, we can also measure its length. So we can say, how far is 7 plus I out? Well, it's 7 squared plus 1 squared, all square rooted. That's the Argand diagram. So when we're looking at the modulus or the length or FOD of a particular complex number, the general formula is that the complex number is written as z equals a plus bi. But the length of it is given as the Darab-Luach, or the absolute value, or the length of that value z there. And that's the absolute value of a plus bi. And that's given as the square of a squared plus b squared. It's not minus, it's a squared plus b squared, even though you might think that I by I is minus 1. It's a distance. So let me just show you how that would work on the diagram. Let's imagine you're asked to calculate the length of 3 plus I. So 3 plus I, you put these bars on it, and therefore the square is 3 squared plus 1 squared, which is the square root of 10. So looking at that on a diagram, here is the point 3 out and 1 up, 3 plus 1i, or 3 plus I. And how far is that from there? Well, it's this squared plus this squared, all square rooted. You don't take that distance, it is a physical distance, so we're talking about a squared plus b squared. So that's the Pythagoras theorem, and that's the modulus. Now, you'll see what's happening here. Sometimes mathematics can be a little bit unfamiliar. Like, you're used to things like plus and minus. You're used to things like dy dx. You're used to things like percentages. But when it comes to complex numbers, we're picking up things like these absolute values. Absolute values is the length of. So those two symbols there, remember, it's just a new letter in your alphabet. We just need to fill it in and say, oh yeah, I know what that is. And there'll be a few more of those along the way. So there's the Argand diagram, and you're asked, there's 7 plus I and 12 plus 5I. Now, if this is Z2 and this is Z1, if you were asked which is bigger, which is longer, which is the bigger absolute value, really the question is which is further from 0 plus 0I. And for you to go from here to here is further than from you to go from here to here. Imagine a circle. That circle is further out than this circle. So that distance is further than this, and that absolute value will be bigger than this. And if we were to do it, we'd get 12 squared plus 5 squared. Whatever that would turn out to be, I think it's 13. And this is 7 squared plus 1 squared, which is the square root of 50. And the square root of 50 is not much more than 7. So that is bigger than that. Okay, so that's complex numbers. That's what they are. And you're asked very often to place them on an Argand diagram. And you get marks for that in the exam just to put them down. But what can you do with complex numbers? Well, what you can do with complex numbers is you can add, subtract, and multiply them. You can also divide them, but we'll do these first, these three first. Complex numbers are really in two parts. So this is the real part, and this is the imaginary part. But in effect, you might think of them nearly as apples and oranges. If somebody said, what's 3 plus 4i and 2 minus I, or 2 plus 2i, you might say if you had 3 apples and 4 oranges, and somebody else had 2 apples and 2 oranges, and you put them all together, well, you'd add the apples together and the oranges together. So you add the real parts together and you add the imaginary parts together. So it's just a question of pairing those two things together. So we're going to do this with addition, subtraction, and multiplication. So here we have a complex number 1 plus 3i, and v is 4 plus 2i, and we're asked to add the two together. So we can write 1 plus 3i plus 4 plus 2i, writing them out. But this number here is real, and this number here is real, and the other two are imaginary. So joining the two real bits together, I get 1 plus 4, like the apples, and the 3i plus 2i, like the oranges. So 1 plus 4 is 5, and 3i plus 2i is 5i. Or I could have done it this way, 1 plus 3i, 4 plus 2i, added up the reals, added up the imaginaries, and that's how it would look. And that's the addition of complex numbers. So here we have the point 1 plus 3i, 4 plus 2i, and if we add them, we get this number here. So it's almost like if I go out 1 east and 3 north, and then after that I go out 4 and 2, I end up there. Or I could have gone 4 plus 2i and then 1 east and 3 north, and I would have ended up in the same place. So u plus v is the same as v plus u. Doesn't matter how you add them up. The two complex numbers add up to the same thing. So there you've got u plus v, or v plus u, all ending up in the same place. So now let's look at subtraction. Subtraction is where you've got a number. You did subtraction before in primary school with just ordinary numbers. Now you're doing them with complex numbers. So complex numbers, we're saying z1 is 5 plus 5i, and z2 is 1 plus 3i. So you're given these two numbers. So if somebody had 5 apples and 5 oranges, and somebody wanted to borrow 1 apple and 3 oranges, how many would be left? So you've got 5 plus 5i, and you're taking away 1 and 3i. So z1 minus z2 is 5 plus 5i minus the other. So the minus 1 goes in there and the minus 3i. So that's writing it out there. But the 5 is real and the minus 1 is real. So I'm going to join those two together. And the 5i and the 3i are imaginary. And I'm going to join those two together. 5 minus 1 is 4. 5i minus 3i is 2i. 5 minus 3 is 2. Again, I could subtract them there. 5 minus 1 is 4, and 5i minus 3i is 2i. Again, if I'm out here at the point 5 plus 5i in real and imaginary, and I take 1 plus 3 from it, I end up with 4 and 2i. If I take 4 plus 2i from it, I end up way back at 1 and 3i, and all the way. And that's how we represent it. Apologies, the page are just sticking together, I'm afraid. Now, this is an interesting thing. We're talking about multiplying two complex numbers together. So let's imagine you've got this point here, 1, 1i, and the point 3 and 2, 3 plus 2i. What happens when you multiply this number by this number? How does that work? So we're going to start 1 plus I by 3 plus I, different numbers. So Americans use a thing called they call it the FOIL method. They start with the first. So 1 by 3, then the outsides, 1 by I, then the insides, I by 3, and I by I. So 1 by 3 and 1 by I by 3, and I by I. So 1 by 3 is 3, 1 by I is I by 3 is 3i, and I by I is I squared. Now the definition of I is that it is the square root of minus 1. If you square it, you have to be able to square this. And if you square a square root, you end up with minus 1. So in this situation, I squared really is minus 1. So the numbers are 3 plus I plus 3i minus 1. Now if we look at these from a real and imaginary point of view, 3 is a real number and minus 1 is a real number, but these are not. So the 3 and the minus 1 we put together to make 2, and the I and the 3i we put together to make 4i. So really what we're finding is we can multiply two numbers together and get another complex number. So when I multiply this number here, 1 plus I, by this number here, 3 plus I end up with this number here, 2 plus 4i. So I can now add, subtract, and multiply complex numbers. So there's the I, 1 plus I, there's the 3 plus I, and there's the 2 plus 4i. So at the moment, we'll just take it as numbers. We'll take it that, yeah, complex numbers do this, there's two parts, you multiply them together and whatever. But later we'll see something really interesting about how multiplication of complex numbers work and really the magic behind them. And there was a famous Dublin mathematician, Rowan Hamilton, and he was very much involved in all of the equations around complex numbers. He was so taken by them one day when he was out for a walk that he actually chiseled his thoughts into a stone bridge on the canal in Dublin, and people go every year to commemorate and look at what was scratched there to commemorate his work in complex numbers. But as I said, you're using them daily. On every day you're using complex numbers very many times. But I'll explain later. Complex conjugates and division. When it comes to division of complex numbers, you need to do a little trick because it's very hard to divide by a complex number without taking a step in the way. So here we're going to take an example of a complex number, and the standard one is Z, complex number, A plus BI, where A is a real number, B is a real number, and I is imaginary. Now, the complex conjugate is denoted by this strange symbol on the top, Z bar. Looks nice. It just says it's related to Z, it's a complex conjugate or a twin, and it's sometimes written A plus BI like that. But it's actually the same number A, but the minus in the b. And the great thing about these complex conjugates or twins is that when you multiply them by each other, or when you add them to each other as pairs, they end up with a real number. So let me explain this. Imagine the complex number 3 plus 4i over here, 3 out and 4 up. If that's Z1, Z1 bar has the same 3 out, but the opposite on the imaginary part. So it's the mirror image. Imagine this being a mirror, and you're looking into the mirror, and you see down, and you get the opposite, the image of it. So Z1 bar and Z1 are mirror images. Z1 doesn't have to be on the top. This could have been Z1 and that's Z1 bar. Here we look at this one, and let's call that Z2, minus 1 and minus I. And Z2 bar, that's its mirror image. So you look in the mirror and you can see the opposite on the other side. You look in. So let's add complex conjugates together. Let's add 1 plus 2i to 1 minus 2i. 1 and 1 gives you 2. 2 and minus 2 gives you nothing. So there's not I. Here's the number 1 plus 2i, and here's its twin on the bottom, the u bar. So if you went out, say, 1 east and 2 north, and then you went out 1 east and 2 south, you could see here that you'd be cancelling each out. You'd end up here as the answer. 2 plus 0i is on the real number line. It's not out there in space. It's exactly here. So 1 plus 2i is here. 1 minus 2i is here. Add the two together, and those bits cancel, and you end up here. Now let's multiply them together. Let's multiply 1 plus 2i by 1 minus 2i. 1 plus 2i by 1 minus 2i. We use the FOIL method first, 1 by 1. Outside, minus 2i. Inside, plus 2i. 2 by 2 is 4. Minus by 2 by minus is minus, and I squared. So that's 1 minus 2i plus 2i. Now, I squared is minus 1. So that's really minus 4 times minus 1. So it's 1 minus 2i plus 2i plus 4. Now I can look at the imaginary parts and the real parts. The real parts are 1 and 4, which is 5. The imaginary parts are minus 2 and plus 2, so they cancel. So I end up with 5 plus 0i. So what this is saying is if I multiply that number by this number, I end up there. So that by that brings me over there. Don't necessarily see why, but it does, and I'm happy with that for the moment. And now we look at division. We haven't done division yet, but we're going to show a trick in division using the complex conjugate. So this is standard enough for the questions on the program. You often get a division. So calculate 1 plus 8i over 2 plus 3i. So it's very difficult to divide by this. So what we do is we use a trick and we multiply above and below by the complex conjugate of the thing on the bottom. So we write down 1 plus 8i over 2 plus 3i exactly as before, and we multiply it by 2 minus 3i above and below. If we multiply by above and below by the same thing, we're not changing anything. But 2 minus 3i and 2 plus 3i. So for some practice, you might help me with this. On the top line, I've got 1 plus 8i by 2 minus 3i. And on the bottom, I've got 2 plus 3i by 2 minus 3i. And you might just multiply those out and see what you get. So take a minute to do that, okay? So 1 plus 2, 1 by 2 is 2, 1 by 3i is minus 3i, 8 by 2 is 16i, and 8 by 3 is 24i squared. The minus 24i squared, that's 2 minus 3i plus 16i plus 24, because the I squared would be minus 1. 2 and 24 added together gives me 26. 3 and 16, well, minus 3 gives me plus 13i. That's what I got on the top. On the bottom, 2 by 2 is 4. 2 by minus 3 is minus 6i. 3i by 2 is plus 6i. 3 by 3 is 9. 3 by minus is minus 9i squared. So that's 4 minus 6i plus 6i plus 9, because I squared is minus 1. The 4 and the 3 come together to give me 13, and they cancel because they're equal. And that's good, because I would have wanted the bit on the bottom to be just a real number, because I don't want any imaginaries in it. That's why I introduced that trick of the complex conjugate. So effectively what we've got is, after all of that, and they're in the notes there, you can go through them step by step, but you can see what I did. I multiplied them out in the FOIL method. I had all the various pieces. I then went through and joined the bits up together, and I ended up with 26 plus 13i on the top and 13 on the bottom. And if I divide 13 into 26, I get 2. 13 into 13i, I get I. So effectively what I've got is this number here, 1 plus 8i, divided by this number here, gave me this number here, which is interesting. Okay, and that's division that's how it would work out. So you can take a complex number, divide by another complex number using that complex conjugate trick, and you get the actual answer then. Now, to show you the trick and what's all happening here, and the observation and how complex numbers are useful to you. When multiplying complex numbers by each other, they found that when you multiply Z3, when you get two numbers, Z1 by Z2, and call it Z3, the angle of the product is given by the sum of the other two angles. Now, what does that really mean? It really means that if I've got a complex number here, and I'm going to draw one here briefly, and it says if I've got a complex number here called Z1, and I have another complex number here called Z2, if I multiply them one by each other, this one by this one, the theta 1 here, this angle, and this angle here, the resulting Z3 was both of those together. So Z3 was up there, which was great. So they found that when you multiplied complex numbers by each other, the angles added. The angles they made with 0, 0. They also find when dividing complex numbers by each other, when Z is Z1 over Z2, the angles were subtracted from each other. So the angle you got in Z3 was the first angle minus the other angle. So for example, if I go back to the recent division we did, this one here, that if I take the original angle of this one and call that theta 1, and divide it by this angle here, theta 2, that divided by this brings me down to this angle here, theta 3. This is this minus this. So theta 1 minus theta 2. So dividing, I bring the angle down. Multiplying, I brought the angle up. Really what's happening is we're finding that multiplication is doing something pretty magic and division is doing something pretty magic. So let's imagine going back to the number line. If this is the number 1, 2, 3, if you consider it 3 times 2, you say, well, you go out 2, 3 times. So 2, 2 again, you end up with 6. So 3 times 2 is 6. All that happens in multiplication is you go further away. But with complex numbers, when you multiply something by something else, you rotate. So the answer you get is the adding of the angles. The reason it doesn't work with the ordinary numbers is because the angle is 0. So adding 0 and 0, you still end up on the number line. But here you're talking about rotating. Dividing, if I'd say 6 divided by 3, okay, I get 2. Dividing, the angles go the other way. So in one case, I rotate clockwise, and in the other case, I rotate anti-clockwise. Anti-clockwise for multiplication, clockwise for division. So that's what they spotted. When dividing by complex numbers, you subtract the angles. They also said when you multiply two complex numbers by each other, the moduluses, these were they called the absolute values or the Darab-Luuk, the full absolute values. Z3 is Z1 times Z2 in terms of its lengths. So the bigger Z1 is, the bigger Z2 is, the bigger Z3 would be. And similarly, when dividing complex numbers, the modulus turned out to be the first one divided by the second. So the size changed as well. So if we look at multiplication, here's 3 plus I times 1 plus 2I. We can see the length of that and the length of that. Multiply the two together, the length gets bigger, much bigger. But it also rotates. So we can see that that was an angle here, we could work it out. That's an angle, we can work it out. And that's another angle, we could work it out. If we wanted to work it out, we could. 3 plus I think we go out here 3. We go out here 1. I think we would know that's 1 and that's 3. And if somebody asked you for that angle, you could say 3 squared plus 1 squared is the square root of 10. What's that angle there? Well, I don't know, but the angle, I don't know, let's call it theta. But that is opposite theta, and that must be the adjacent. So opposite over adjacent, 1 over 3. So tan of theta is 1 over 3. Theta would be equal to whatever. So we could find that angle. And we can find that if we get that angle and the next angle and add the two together, that's the angle we get when we multiply. And similarly, when we divide, dividing turns it this way. So why is all this important and when did we use it today? Well, just imagine if I multiply something by I. I'm going to multiply the number. So just watch this for a second. 1 plus 0I. And let's say I multiply that by I. Or not even I, 0 plus I. So I've got the point here, 1 plus 0I, and this point here, 0 plus I. So this is 2 plus 0I, and that's whatever, minus 0 minus I. So if I multiply this number here by this one here, what do I get? So 1 plus 0I by 0 plus I. I'll use the FOIL method. First is 1 plus 0 is 0. 1 plus I is I. Sorry, 0 by 0 is 0. And 0 by 0 is 0. So I just end up with 0 plus I. So if I multiply this by that, I end up there. If I were to multiply it again and say what's 0 plus I by 0 plus I, 0 by 0 is 0, 0 by that is 0 I. The middle's now I plus 0 is 0 I, and I by I is I squared, which is minus 1. So I get minus 1 plus 0 I. I'd end up here. What I'm showing here is that if you multiply something by the number I, you rotate every time by 90 degrees. Now, I imagine that all of you have mobile phones, and all of you have looked at pictures on your mobile phone and turned them one way or the other to see a better view. So as you're turning that mobile phone one way or the other, really what you're doing is you're taking the picture and you're multiplying it by an imaginary number and rotating it. Because you're only multiplying it by I, it stays the same shape and size in that sense. If you are multiplying it by something less than I, you would find that you'd get a number like this. If you're multiplying it by something bigger than I, where the z was bigger than, absolute value was bigger than 1, you'd find that it would be going out and about like that. But yes, you've probably used your phone and changed it, or maybe locked it so that it doesn't turn when you turn for the views or whatever. But that's the use of complex numbers on a day-to-day basis, and the mathematics for that go back to the mid-1800s to an Irishman walking under the bridges in Dublin in 1880 or thereabouts. So that's the complex numbers. We'll do some questions from the exams now, but we look at the complex numbers and just see how they might use them and how they might bring them up in various questions. You've covered the course in complex numbers, but just what they might ask you to do. So here's some questions that they could give you. So the first one is just expanding out complex numbers, and they say simplify 3 plus I times 3 by 2I plus I squared. Now, you've probably done a thing called BOMDAS, brackets, order, multiplication, and division. So let's just do that here. If we were simplifying this, we'd work inside the brackets first. And working inside the brackets first, we'd see the I squared as the first thing there because it's a power. So 3 plus I times 3 by 2I plus I squared is really minus 1. We look again inside the brackets, and the next important thing is multiplication, so we do that next. 3 plus I, that's 6I, plus I minus 1. Now we might tidy up inside the bracket by saying the 6 i's and the i's go together, so we get 7I minus 1. And now we've got a number multiplying into the bracket, so we'll do that next. So 3 plus I by 7I is 7I squared, and I by minus 1 is minus I. We now simplify this. The I squared is really a minus 1, so that's 3 minus 7 minus I. Then we bring the real numbers together. 3 minus 7 is minus 4 minus I. And that's your answer there on that. And that's something that you might have to do. They might say multiply something out like that. This is a neat trick. Basically, I said that if you've got a complex number z1 of a plus b I, and you have another one z2 c plus di, the only way they can be the same is if the real numbers are the same and the imaginary numbers are the same. So how would they use that in an exam question? Well, here's the question now that's a bit trickier than you might have expected. You'd say, solve this. S plus ti is 1 plus 3i squared. And you'd say, how would you do that? Well, it's really quite unusual. So you say, well, I don't know, where both s and t are real numbers. So you say, I don't know, but I'm going to do the bit I can do. 1 plus 3i squared is really 1 plus 3i times 1 plus 3i. So again, this is multiplication of complex numbers, so marks for that. Use the FOIL method. So outside 1 by 1 is 1, 1 by 3i is 3i, 3i by 1 is 3i, and 3i by 3i is 9. 3 by 3 is 9, I by I is I squared. So we now have 1 plus 3i minus 9, because I'm substituting there for the I squared. Going to put the two real numbers together. So 1 minus 9 plus 3i plus 3i. And I end up with minus 8 plus 6i. Really it's saying solve s plus ti is this. So how do I solve that? Well, it's telling me that the real number s must equal the real number here. So s equals minus 8. And the t before the I must equal the number before the I. So t is equal to 6. And that's all that was in that question. But when you looked at it, you said, that's a bit tricky. Wasn't expecting that on a complex number question. Here's another question that looks very tricky. You say, oh, I didn't do this. The numbers are a bit strange. The symbols are a bit off-putting. But let's just see how it might be, taking it step by step. K, w plus w bar is 20, where w is equal to 2 plus 5i. W is a complex number, 2 plus 5i, a real part and an imaginary part. But we have to remember that this w bar symbol is the complex conjugate. And the complex conjugate is something like this, but a bit different. It's its twin, the mirror image. So the mirror image is 2 minus 5i. So now we're going to see if we can solve this. K times 2 plus 5i plus 2 minus 5i is equal to 20. We can bring these bits together. Let's take the two real bits together, and we'll say k times 4. But the 5i and the minus 5i cancel. So k times 4 is 20. 4k is 20. How do I get rid of the 4? Divide by 4. K is equal to 5. So that looked like a tricky question, but it actually was reasonably straightforward. Once we said we're going to start, we're going to plug in the numbers, see where it takes us. Here's a further example that they could use. Haven't used it for a while, but they could use it again. And here they're saying solve the following. This looks like quite long to solve. And we look at x into 1 plus 3i plus y into 2 minus I plus 2 plus 3i is 7 plus 4i. What we have here are real numbers and imaginary. We have a real and imaginary here, and we have to have real and imaginary here. So we can work it out. So let's just plug the numbers in. That's x plus 3xi plus 2y minus yi plus 2 plus 3i equals 7 plus 4i. Now there's a lot going on in that. You say, where is all this going? Well, let's just look at the real for the moment. What's the real saying? The real numbers have no i's. So let's look. We say that's x plus 2y, because that's real, and that's real, and the 2 is real, plus 2 is equal to 7. And the imaginary, if we add this, we get 3xi minus yi plus 3i is 4i. Now, if we look at the first equation here, x plus 2y plus 2 is 7. If we took the 2 over to the other side, we get x plus 2y is 5. If we took the next one, 3xi minus yi plus 3i is 4i, and took all the i's out of it, we'd get 3x minus y plus 3 is 4. If we took the 3 over to the other side, we get 3x minus y equals 1. If we look at the two of those equations, we can see they are two simultaneous equations. Simultaneous equations, you've solved those before, you can solve them again. So really, what they're doing is they're showing how you can get two simultaneous equations hidden away in that. And that's how you would solve that. So what else can they ask before we go through exam questions? And the exam questions have been generally very straightforward, very easy to do, very quick to do, and you know you're going to get all the marks. So let's look at the roots of polynomials. Here's a graph, standard graph. It's a quadratic graph, and you can see that it cuts the x-axis in two places. The green one, slightly above it, is a perfect square there, and it cuts just touches the x-axis just once, whereas the red one doesn't touch at all. In effect, this has got no real roots. It's actually got complex roots. So for example, if we looked at this one here, x squared minus 6x plus 12, and instead of x we use z squared minus 6z plus 12. And if we wanted to find the roots where that crossed the x-axis, we'd say, I don't think it does really. I think it's above it. So we could use the minus b equation from before. Remember that the a is the term in z squared, the b is the next one, and c is the coefficient on its own. So a, we say that's the number 1 because there's only one of them there. B is minus 6 and c is 12. So I've written down the numbers and the formula, and I'm going to go to the next page and use them. I'm going to write down the minus b plus or minus and copy the numbers in. So for minus b, I'm going to say minus 6. Plus or minus the b squared, I'm going to put my minus 6 in there. Minus 4 times a by c over 2a. And I do all this, but for the first time, I'm seeing that I'm getting the square root of minus 12. The square root of a negative number. So that tells me that it's not going to be real roots. This curve is not going to cut the real graph. It's going to be up here somewhere. So I'm looking for complex numbers. So the square root of 12 minus 12 is actually the square root of minus 1 by the square root of 12. The square root of minus 1 by the square root of 12 is actually the square root of 4 by the square root of 3. And the square root of 4 is 2. So let me go through that again so you know how the square roots work. Okay? If somebody says, what's the square root of 16? I think you'd say 4. But the square root of 16 is really 4 times 4. So the square root of something like that, that gives us the 4. What happens when we do something like the square root of 12? How do we do that? Well, the square root of 12 is 4 by 3. Okay? So therefore, what we can do there is, rather than taking the square root of 4 by 3 is the square root of 4 by the square root of 3. And the square root of 4 is 2. So 2 root 3. Similarly, if somebody says, what's the square root of minus 1? It's I. What's the square root of minus 4? Well, that's the square root of 4 by the square root of minus 1, which is 2 times I. Okay? Because 2i squared would be 2 by 2 would be 4, I squared minus 4. So that's how it works around. So that's how you can deal with these square roots. But really what we're showing there is that the square root, instead of being a real number, is an imaginary number. So what might they ask you to do? Well, this is a long question. I haven't seen this for a while in terms of it hasn't been popular in recent exam years. But it's there. It's still on the syllabus. So f of z is z squared minus 6z plus 12. And they're saying, show that when z is equal to 3 plus root 3i, that you get the answer of 0 plus 0i. Prove that it's a root. So what you've got to do is everywhere you see the letter z, you've got to put in 3 plus 3i. So where you've got z squared, you say 3 plus root 3 squared. 6, you say 3 plus root 3i plus 12. So what I do in this slide, and you can look at it later, I put in the value, I make it square minus 6 plus that. I multiply it all out using the FOIL method. I bring all the bits together and I show that it's 0 plus 0i. Okay. Now it's an important point for your exams that if one of the roots is 3 plus root 3i, the twin will always be there as well. So the other root will be the minus 3i. So if one complex number goes in, the complex conjugate will be as well. So if they're the roots, if somebody says z is equal to 3 plus root 3i, then z minus 3 minus root 3i is a factor. This is the root. If you remember at an earlier session this morning, we said if x minus 4 is 0, and that's a factor, x equals 4 is the root. So in complex numbers, if z equals that is the root, this must be the factor. So if you were to ask for the factors, you could multiply the two factors together. That's an awful lot of calculations there. That's a, b, and c by a, b, and c. So if you'd work that out, you multiply the z by the first bit, get z, then the minus 3 by all of it, and then the minus 3i by all of it as well there. And you multiply it all out, and you get your answer there. So basically that's how you do your calculations on the roots. So let's look at some exam questions before I finish. Okay. So that's another formula. Some people use the roots and they learn by, that's another method you can use. You can say, if you know the sum of the roots and the product of the roots, you can get it as well. But let's go back through it here. What we're saying is that if z1 is equal to 3 plus 3i, if that is a root, and z2 is equal to 3 minus 3i, and that's a root, find the equation. So what you do is you say z1 minus 3 minus 3i by z2 minus 3 plus 3i, and you multiply them out, and that's it. And you multiply and you get that long equation there, and you can go through that and you can see how the calculations are done. To bring it back to a simpler example, if somebody said if x equals 4 is a root and x equals minus 2 is a root, you'd say x minus 4 by x plus 2, and you'd calculate it. It just looks a bit more awkward when you've got two parts in the complex number. So if they tell you what the root is and they tell you what another root is, you can multiply the two out and get the whole factor. So that's it. We leave it at that for now. So let's we'll take a break and we'll go through the recent exam questions in complex numbers. And as you can see, they're quite short. So thank you. We're going to look at the exam questions from 2019 and 2020. The complex number Z1 is 2 plus I is shown on the Argand diagram. Find Z2 where it's 2 times Z1. So they're telling you that Z1 is 2 plus I, and they want 2 of them. So effectively all you have to do there is Z2 is 2 times 2 plus I. 2 times 2 is 4, 2 times I is 2I, and that's Z2. And you say that must be 4 plus 2I here, and that's Z2. Find the value, label it, and draw it on the graph. That's it. The next one is Z1 bar is the complex conjugate. Write down the value. So if Z1 is 2 plus I, Z1 bar is 2 minus I. 2 minus I. Investigate if Z2, the modulus, the length of, is the same as Z1 plus Z2 bar. So what have you got to do here? You've got to work out the modulus and you've got to do addition. So let's do the first bit and let's look at Z2. Z2 is 4 plus 2I. 1, 2, 3, 4, and 2I. 4 plus 2I. What is Z2 bar? Z2 bar is the length from here to here. It's the length of the hypotenuse. So really what we're saying is, this is 4, this is 2, what's this? If this is a right angle. Pythagoras would say it's 4 squared plus 2 squared, square root it. Or the formula is a squared plus b squared, square root it in your tables. So you say it's 4 squared plus 2 squared, square root it, and you say that's 16 plus 4, which is the square root of 20. Now the question you were asked was, I think, investigate if the length of that is the same as Z1 plus Z1 bar. Z1 was 1 plus 2, 2 plus I think. Z1 bar is 2 minus I. Add the two together, 2 plus 2 is 4, and you get 0, which is just 4. So the length of Z1 plus Z1 bar is just 4, and 4 is not equal to the square root of 20, because that's bigger. So investigating it, you said, I investigated it, and they're not the same. What else did they ask? Show that Z1 is 2 plus I is a solution for this. This is what I was talking about putting in the equations into roots there. So this is a straightforward one. Z is 2 plus I. And they're saying, does that fit into z squared minus 4z plus 5 equal to 0? Does f of z, 2 plus I, fit in here? So we'll do this one slowly. We'll say everywhere there's a z1 or a z, I'm going to put in 2 plus I. So 2 plus I squared minus 4 times 2 plus I plus 5 equals 0. So I now have to work through that. 2 plus I by 2 plus I is equal to 2 by 2 is 4, 2 by I is 2I, 2I is 2I, and I by I is I squared. Adding those up together, that's 4 plus 4I minus 1, or it's 3 plus 4I. That's the first part of it. The second part of it is here. So that's going to be minus 8 minus 4i plus 5. So let's see how that works. I've got a 3 minus 8 plus 5. In terms of real numbers, 3 minus 8 is minus 5 plus 5 is naught, and the 4i and the minus 4i cancel. So what I've proven there is that when I put in z1, that number, into this, I find that it's 0. If it's 0, z1 is 2 plus I is a root, z1 minus 2 minus I is a factor. And that's the full marks for that. And we were only in there a few moments. And I think this is the very last, or maybe thereabouts. Yes, I think this is the last question. So we should be finished a little bit earlier, which is great. So here we have final question. And complex numbers come up every single year, so there will be a nice question on it. Z1 is 3 minus 4i. Z2 is minus 2 plus I. Z3 is 2i times Z2. So you'll see there that to get Z3, I've got to take 2i times minus 2 plus I. So I have to be able to multiply one thing into another. So 2i by minus 2, 2 by 2 is minus 4, and that leaves the I. And 2i by I is 2i squared. The I squared makes that a minus 1, so it's plus 2 times minus 1, or minus 4i minus 2. So it looks like Z3 is minus 2 minus 4i. Now I did that, they haven't asked for it yet, but I'm sure they will. Write Z3 in the form of. So the first thing they wanted me to calculate was Z3. So we've done that. Plot Z1, Z2, Z3 on the Argand diagram. So again, marks for that. Z1 is 3 minus 4i. So 1, 2, 3, 1, 2, 3, 4. 3 minus 4i is Z1. Z2 is minus 2 plus I, which is here. And Z3 is minus 2 minus 4i. We don't have to put in the lines, I'm just pointing them out, that's where they are. Okay? So label each point clearly. That's Z1, Z2, and Z3. Okay, minus 2 plus I, minus 2 minus 4i, and 3 minus 4i. Find Z1. So what they're saying there is find Z1 bar. We have to remember that that means the absolute value, that means the length, that means the distance from 0 out to here. So it's this distance here. So it's 3 minus 4i, and the result would be 3 squared plus 4 squared. It's always the plus, whether it's minus or plus there, it's always plus, because it's 3 out and 4 down. So 3 squared plus 4 squared, that turns out to be 5. Find Z1 bar. Now, very last, if Z1 by Z4 is 29 plus 3i, write Z4 in the form of that. Now, what's going on here? They're saying Z1 by Z4 equals 29 plus 3i. But they want you to find Z4. Z4 on its own is what they want on the left-hand side. So for that to happen, you have to get rid of this Z1. So you divide this by Z1, and you divide this by Z1, and they cancel. So what you get is Z4 is equal to 29 plus 3i over Z1. But Z1, I think, you were already told what the answer was. Z1 was 3 minus 4i, because you were told that at the beginning. You were given the value for z1. So what they're saying is calculate that. It's just a way of saying, can you divide one complex number by another? So they're saying, can you divide 29 plus 3i divided by 3 minus 4i. And we go back through the notes, because the notes that we've covered cover all the questions that can be asked. And we say, for dividing, we need to use the complex conjugate. So we're going to multiply that by 3 plus 4i and 3 plus 4i. So it looks like a big sum, but we're going to take the top part, a, and we're going to say, what's 29 plus 3i times 3 plus 4i? And the bottom part, b, we're going to say, what's 3 minus 4i by 3 plus 4i? The one thing we're expecting is that the bottom bit will turn out nice, because there should be no imaginary numbers at the end. 3 by 3 will give me 9. 3 by 4i will give me 12i. 3 by minus 4i will be minus 12i. And the 4 by the 4 will give me minus 16 by I squared. You can see that the two 12s cancel, because there's a plus and a minus there. The I squared is minus 1 by minus 16, so that makes it a plus. So that all thing turns out to be 25, because it's 9 plus 16 is 25. And we have to find out what the top bit is as well. And we can do that if we want. We can say 29 by 3, I think, is 87. 29 by 4 is, I don't know, it's 116 or something. 3 by 3 is 9i. And 3i by 4i is 12, so that'll be a minus 12, or 12i squared. So that turns out to be 87. They add together to give us 125i, and that's minus 12, or 75 plus 125i. Now for our answer, we're dividing everything by 25. So it's 75 plus 125i over 25, or 3 plus 5i. So what have we done? I've gone through the exam questions quickly, but remember, the exam questions are on State Examinations Board. You can find them all. You can also find all of the solutions and all the worked examples. But hopefully what we've done today in complex numbers is to just, refresh it for you if you were already on top of it, or to fill in a gap or two. And hopefully you now know, in terms of your mobile phone where you're using it tonight, and switching from landscape to portrait, or just turning the camera around, that actually what's happening there is you're multiplying by a complex number, the number I. So let's go back. To those who are still there, thank you very much. Thank you for spending the day with me. I really hope the Leaving Cert goes well for you, whether you choose to sit the paper or to choose the calculated grades that you get. Whatever you do, I hope the maths stays with you, and you realise that it's important and it's there for a reason, and that you're good at it, that there's lots you know, and hopefully a few things you filled in and a few more gaps. So please use the resource as you wish, and I wish you the very best of your luck with your exams. And we look forward to a new year when student life can happen again, and students will be on campus and they can get to know each other, and everything won't be virtual. So Gadishin, Mila Buirkus, Gadeshiv Slán, thank you. Stay safe.